Let's talk about something that's kind of mind-blowing when you really stop and think about it. We're diving into the invisible world that makes modern aviation possible, how these enormous jets can navigate the globe, often without the pilots seeing a thing outside their window. I mean, seriously, think about that. A 500-ton machine miles up in the air, in the middle of a storm, trying to find a little strip of pavement. It sounds completely impossible, right? But this happens thousands of times, every single day, all over the world. So how on earth do they do it? Well, it's not magic, but it's pretty close. It's a symphony of really, really clever, invisible technology. Back in the early days of flying, the rule was simple. If you couldn't see, you couldn't fly. That's what we call visual flight. You're literally just looking out the window. But today, well, that's just not how it works. Pilots spend most of their time in what's called instrument flight. That means they are relying completely on their cockpit instruments to tell them where they are, where they're going, and how to get there, especially through thick clouds, fog, or the dead of night. And the secret to making it all work? It's radio waves. They're all around us, all the time, totally invisible. The entire system of modern aviation, from navigation to communication to safety, is built on this incredible, unseen network that lets an airplane see what our own eyes can't. All right, so let's hop on a hypothetical flight. We're rolling down the runway, taking off and climbing straight into the clouds. The first big challenge is simple. How does air traffic control keep track of us? How do they see one single plane among dozens or even hundreds in the sky at the same time? Well, the first layer of this is something called primary radar. Now, the easiest way to think about this is to imagine shouting into a big canyon and listening for the echo. The radar sends out a pulse of radio energy. It hits our plane, bounces back, and the system on the ground calculates our distance and direction based on that echo. It's effective for sure, but it's also really basic. All it tells the controller is that something is out there. Not who it is or how high it is, just a dot on a screen. But of course, there's a much smarter way. That's where secondary surveillance radar, or SSR, comes in. This is a total game changer. Instead of just a shout and an echo, this is more like a conversation. A ground station sends out a signal that's like a question, an interrogation, and a little device on our plane, called a transponder, automatically talks back, replying with all sorts of useful information. And that difference, right there, is everything. Primary radar just sees a blip. It says, hey, I see something. But secondary radar gets a detailed response. It says, I see flight 123 and it's currently at 35,000 feet. This leap from just seeing a dot to having a full-on conversation is what made it possible for air travel to grow into the incredibly safe and massive system we have today. So our flight is safely tracked and we're up at cruising altitude. But now what? How do we get from, say, New York to Los Angeles? You can't just point the nose west and hope for the best. Pilots have to follow very precise, predefined routes. The answer is a system that creates these amazing invisible highways in the sky. All across the country, there are ground stations called VORs. Now just picture each one as the hub of a giant invisible wheel, constantly transmitting 360 separate radio beams, called radials, one for every degree on the compass. They're like spokes radiating out in every direction. VOR stands for Very High Frequency Omnidirectional Range, but what it does is simple. The pilot's equipment locks onto one of those specific radials, let's say the 090-degree radial heading east, and the instruments in the cockpit guide them to follow it perfectly. It's just like driving down a highway with a route number. By flying from one VOR to the next, following these invisible beams, planes can navigate with incredible precision across huge distances. Okay, we've crossed the country, and now for the most critical part of the whole flight, the approach and landing. Let's say our destination is completely socked in with fog. The pilots can't see a thing outside. This, right here, is where the real magic happens. The incredible tool that makes this possible is the Instrument Landing System, or ILS. This is a system right there at the airport, on the ground, that transmits a pair of super-focused radio beams out from the runway, creating a perfect guided path for the plane to follow all the way down. The way the ILS works is both simple and brilliant. It's made of two parts. First, you have the localizer. That's a beam that gives the pilot left-right guidance, making sure the plane is lined up exactly with the center of the runway. At the same time, the glide path beam provides up-down guidance, making sure the plane is descending at the perfect angle to touch down in the right spot. So,
In the cockpit, the pilots are watching their instruments, basically just two needles. Their whole job is to keep those needles perfectly centered. By following the localizer for left and right and the glide path for up and down, they can fly a perfect, stable approach down through the clouds, sometimes only breaking out to see the runway lights just seconds before a smooth touchdown. Absolutely incredible. But what about navigating around things you can't see? Right, flying through clouds is one thing, but flying blindly into a hidden thunderstorm? That's a whole other level of dangerous. So for that, pilots need their own set of eyes on the plane itself.
And that's the job of the airborne weather radar. There's a small radar unit in the nose of the plane that's constantly scanning the sky ahead. Now here's the really clever part. It doesn't actually detect clouds, because clouds are just water vapor. It's designed to detect water droplets, rain, hail, you name it. The denser the droplets, the more intense the storm, and the stronger the radio signal that bounces back to the plane. That information then gets painted on a screen in the cockpit using a really simple color code. Green means light rain, no big deal. Yellow means moderate rain, might get a little bumpy. Red indicates heavy rain and some definite turbulence. But the one they really look out for is magenta. Magenta means extreme rainfall and very likely severe turbulence. Those are the areas you avoid. No questions asked. So when you put it all together, you see it's not just one single piece of technology. It's a system of layers, all working together, all backing each other up. You've got secondary radar for tracking, VORs for navigating the highways in the sky, the ILS for landing in zero visibility, and weather radar to keep everyone safe and comfortable. It's these layers that transform what seems like an impossible challenge into one of the safest ways to travel in the world.
But technology never stops moving forward. We're already in a massive shift away from these ground-based radio systems towards satellite-based navigation, like the GPS we all use in our cars and phones. This is opening up possibilities for even more direct, more efficient routes. And it leaves us with a really fascinating question to think about. As we continue to innovate, what will the invisible highways of the future really look like?